Good day everyone. So my name is THANASEELAN BALAN and today I will present about my assignment for digital communication. My project focus on simulation of QPSK OFDM system. Uh, for the introduction, this presentation explores the design and simulation of QPSK OFDM communication system using MATLAB and Simulink. OFDM is a key multi-carrier modulation technique used in modern high-speed wireless networks due to its efficiency in handling multi-path fading and interference. By combining it with the QPSK modulation, we aim to simulate a complete transmission path from data generation at transmitter to signal recovery at the receiver and evaluate how different noise injection methods such as basic Gaussian sources and proper AWGN channels affect signal integrity. So the question is, figure 1 shows the assignment instruction. This was my starting point. So the goal was to complete the circuit and then perform two specific tasks. First one is using the basic Gaussian random source, and the second one is using the AWGN channel to test SNR values, which is I use 5 dB, 10 dB and 15 dB. So now I will demonstrate the simulation in MATLAB. First of all, I have to write a code in the command prompt for the task 1 and task 2. So emblem f equals to 100, m equals to 4, s time equals to 1 micro, and r and seed equals to 10. I run this command in command prompt and then we move to the task 1. So this is my diagram for the task 1. As you can see here, the first Simulink model, I have completed the transmitter using the Bernoulli binary generator and the MPSK modulator, MPSK demodulator. For the Gaussian random source, this one I am using the source type Gaussian. For task 1, I followed the diagram exactly, splitting the signal into the magnitude and angle and adding noise to the magnitude part. So we run the simulation first. So if we see the constellation diagram, diagram 1 and 2 and 3, we can see the noises scattering the signal. So at the output receiver, it's making it difficult for the receiver to map the points exactly. It's outside the plus points. For the task 2, let's look at the modified system using the AWGN channel. So I removed the splitters so the signal flows directly to the channel block. One very important thing I discovered here is the power settings. So before I set the SNR values, I have to change the input signal power reference to 1 ohm to 0.01. Because if we use the 1 watt, the noise is too strong. So I set the input signal power to 0.01 watts, and if we change the SNR value to 5 dB, apply, then OK, and then if we run this one, so at the 5 dB the constellation points are very messy. So if we have to change the value of the SNR to 10 dB. So we can see at the receiver side, the clusters are start to tightening at the plus point. This one for 10 dB, and if we change the value again to 15, we can see the fully tightened one. We can see the results. It's tightening up beautifully on the receiver's end. This proves the system is recovering the data correctly from the AWGN channel. Now let's move to the discussion and the conclusion part. So the results clearly demonstrate the relationship between the signal to noise ratio SNR and signal recovery. In the initial task, we observed how the manual noise injection impacts the signal's magnitude. However, the upgrade to a dedicated AWGN channel provided a more realistic evaluation. The critical finding during this simulation was the necessity of adjusting the AWGN input signal power to 0.0 watts to compensate for the mathematical power drop inherent in the IFFT process. Once correctly calibrated, the constellation diagrams show a clear progression. At 5 dB, the signal was heavily distorted, while at the 10 dB and the 15 dB, the receiver achieved nearly the perfect recovery with tight, distinct symbol clusters. In conclusion, all project objectives were successfully achieved. Through this simulation, I have gained a practical understanding of how IFFT and FFT blocks facilitate OFDM transmission and the importance of precise power tracking in digital communication models. By comparing the basic random source with the AWGN channel, I successfully verified the IASNR levels, directly improved the receiver's ability to accurately demodulate the signal. The functional model confirms that the QPSK of the system was correctly mapped, transmitted, and recovered under varying channel conditions. That's all for me. Thank you.